Hopefully by now you've completed the quiz on Canvas about why stats and done some of those activities so that you'll understand what we're talking about here. But basically what I gave you, wow, this looks horrible. But anyway, if you can kind of see the X's, I gave you two things and we were trying to figure out if either the basketball players making free throws or the coins, and I put an X for a head and a dot or a dash for a tail. But when we think that this is basketball players shooting free throws, we know that players can tend to be streaky. In other words, if they get on track, they might make several in a row, and then if they're a little off, they might miss a few in a row. And so in doing so, we kind of start to see trends. Oh, that person kind of hit a bunch in a row, and so forth. We start to see trends where the trends are not there. And this is partly because humans are very good at seeing trends. Part of our brain and part of what makes us very good analysis and things like that is because we can see where trends are. As we can see here, showed any trend. And what I didn't tell you was that both were actually just simply coins that I'd. But it also means that we have a tendency to be able to see trends really well, and we can kind of think there are trends even if it's just completely random. So both of these were random. And this is one of the reasons we need statistics, because we need to find an objective way to really determine if there is a trend. So if we think that drug A is going to kill tumor cells, we need to see if there's a real trend towards reducing that growth, or if it's just something that we are starting to see. And if we have replicates and so forth, are the replicates showing us a consistent trend, or are they just random all over the place? So we also saw this with the 90% confidence quiz. So we tend to be more confident than we should be. So there was no reason for you not to have a huge range if you weren't sure. So if you didn't know Martin Luther King Jr.'s age when he died, and you really had absolutely no clue, if you don't even know who Martin Luther King Jr. is for some reason, hope that's not the case, but if that's the case, you might be able to put in, okay, that person must have died somewhere between age 0 and age 100, and you're probably 90% going to be correct. But we start to put in ranges because we think we know a little bit better than we do, especially with some of those other ones. I would have no clue how many countries are in OPEC. This is the oil-forming conglomerate. The diameter of the moon, I'm not sure. But you can make these ranges wide so that you have a 90% chance of the actual value being in there, but we make them smaller than they actually are. And I showed you in the feedback on the quiz, if you paid attention, that when this was given to a lot of people nationwide, 99% of the participants were overconfident. So in other words, if you were accurate in your 90% interval, you should have had 9 out of 10 be within that, fall within the intervals you gave. That's a 90% confidence. 9 out of 10, yes, 9 out of 10 times you would be correct if you have a 90% confidence. But 99% of participants missed more than 1 out of 10. So in other words, they weren't accurate when they thought they were being 90% confident. And in fact, the majority had less than half of the answers fall within that range. Right? So when they thought they were 90% confident, they were actually less than 50% confident. And this seems to be true for questions that are within someone's area of expertise as well. They tended to give smaller ranges because they were experts, therefore they thought they knew really well, but again, they were overconfident. So this is another reason we need stats, because we are overconfident in what we're doing. And if you think about it, there's a reason you are testing a hypothesis, right? You have a hypothesis because you believe the background data, your observations, you believe everything shows that to be likely to be true. You think that's a good explanation for those observations. Otherwise, you wouldn't be testing it. You wouldn't be wasting your time and money in that regard. So you think that hypothesis is true. And this, no matter how ethical you are, this gives us bias. Right? So we are biased in between the fact that we are overconfident in what we think. We tend to see trends when there's not trends, especially if we think we know the answer. We're going to be biased towards that hypothesis being correct. And there's no way around that. This is one of the reasons you have to have blind tests or masked tests where neither the doctor or the patient knows if they have the drug or the placebo, etc., because we are overconfident. And this is why we need stats. Stats is an objective way to look at the data and determine what that data is telling us. So how do we do this? Well, the key thing to remember here is that there are two aspects to data. There's the average, so if you have replicates, there's the average of that data, and then there's the standard deviation. So here I have two data sets, right? So data set 1 and data set 2. And you can see that, well, let me ask you, what is the average of each of these data sets? I'll tell you that the average for both of them is 10. So the average for both of these data sets is 10. And here's how I know. Well, here we have 10, 10, 1 above 10, and 1 below 10. 1.5 below 10, and 1.5 above 10. That means it's going to average out to 10. Well, down here we have 6 below. This 6 below is averaged out by that 6 above. This 3 below is averaged out by that 3 above. And then we have 10, 10. So the average of both of these data sets is 10. But does that mean they're the exact same data? No, obviously not. So which of these would have the greatest standard deviation? So since standard deviation is a measure of the variability of the data, in other words, how much does each data point vary away from the mean, data set number 2 is going to have a much higher standard deviation. It's a much higher variability in that data set. All right, and that makes that data very much different from each other. Even though the averages are the same, even though the averages are both 10, these data sets mean very different things because the variance, the standard deviation, is different. And here's kind of what we're talking about, standard deviation. So the first data set, where all the data points were really close to 10, would be like this red set here. So that variance is very, very low. The data's all near that. And then if you have data that varies quite a bit, your range and variance is going to look more like this blue line. And so standard deviation is basically a measure of what intervals would you be confident in knowing that 66% of the data is going to fall within this. So based on the data we have, if I did one more data point, there's a 66% chance that it would fall within this range. And then if you have 2 standard deviations, there becomes a 95% chance that any new data point you pick would fall within that range. All right, so standard deviation is basically giving us real data-driven confidence intervals for how much our data ranges. And this is very important because here we have a control group and a treatment group. And really what we are trying to figure out is if the control group is different from the treatment group. Right? So for example, if on the x-axis we had amount of cell growth, and we had a control group, and we had a test group, we want to know if maybe the test group is where we added a drug. We want to know if the drug really made a difference in those two. And there's going to be variation. So the number of the amount of time we do this, we're going to have different number of cells. Each replicate is never the same. Anyone who's done science, you know that you can do the exact same thing 2 times and you're not going to get the exact same data. There's natural variation. All right? So if we take a look over here on the right, my question for you is, which of these data sets would you be most confident in saying that there is a true difference between the control in green and the test? All right, so you have A, B, and C. Well, C definitely has the highest probability of there being a real difference between these two groups because there's less overlap in the groups. The variability is less between all of them. The differences between the averages, shown by these dotted lines, the differences between the averages are exactly the same for A, B, and C. Right? So the differences aren't telling us, in this case, which ones are more likely to be different. The variation plays a really important role as well. So we need to have stats. Right? So we need stats that take into account two things. One, the difference in the averages. All right, so if I had two groups, and one group was down here like this, and one group was way up there like that, then the bigger the difference between the averages, the more likely there is to be a real difference. However, if I had another set where I had two groups like this, if I have big error bars, there is much less likely to be a difference between those groups than if I took the same data and had smaller variability. So we need stats that take into account the difference in the averages and the variability of the data. And so I'm just going to draw kind of that one more time. Again, if we have two data sets and both of them have the same differences in the average, so I'll draw in a bar graph this time instead of that graph. One of them has huge standard deviations and one of them has very small standard deviations. I am much more confident that that is a real difference because the variability is less. So both average and standard deviation or variability matter. So we need stats that take both of those into account. All right, so let me get rid of that drawing and let me talk to you a little bit about what we're doing with this. So in science, we have two types of errors. All right, so we have an error where the null hypothesis was true. So remember, H naught is null. So that's our null hypothesis. So it means there was no, it's saying no difference, right? So the null hypothesis was true, but we rejected it. That's a type 1 error. All right. We also have errors where the null hypothesis was false. So in other words, the real hypothesis was true, but we didn't reject the null hypothesis. That's a type 2 error, right? So we are much more worried about these type 1 errors. These are bad in science, all right? So think about it. If we have data that shows a real difference, but we don't reject the null hypothesis, that just means oftentimes that we need more data, right? It just means that we have not yet gotten the amount of data to reject the null hypothesis with a high enough confidence, right? But if the null hypothesis is true and there really is no difference and we reject that, that's a problem. So think about it. If we have two drugs and one of them is able to kill cancer and one of them is not, but the one that's not able to kill cancer, that would be the null hypothesis accepted. There's no difference between the control and that drug because it doesn't work. But if we reject the null hypothesis, we're saying there is a difference. And now suddenly we're giving people that drug that doesn't work. And they're thinking that drug works, and they're taking a drug, they're paying for a drug, they're putting their health on the line for a drug that doesn't do anything. So when we reject the null hypothesis and say this is a real difference, we want to be very, very confident in that. So we really do not want to have type 1 errors. We want to be very confident if we reject the null hypothesis that our data is real. And that's why we go for those 95% confidence intervals. For example, you can think about a type 2 error. Maybe our p-value is 0.1. That really means there's only a 10% chance the null is correct. But we still don't reject the null because we want a 95% chance that the null is incorrect. That's why our p-value level is less than 0.05 in order to reject the null hypothesis. There's a less than 5% chance that the null is correct. Therefore, we know a greater than 95% chance that the real hypothesis is true. That means we're trying to make sure that there is a less than 5% chance of making a type 1 error. Because we don't want those. We want to be 95% sure that our data is real before we reject the null hypothesis. We want a less than 5% chance of a type 1 error. If we got a p-value of 0.1, if we did more data, that p-value might go on lower. So this just kind of tells us, yes, there's a trend. There's a less than 10% chance that null is correct, but we need more data to get to that 95% level. All right, so let's think about this with regards to sampling error. So this is variation in a set of data that's really just due to random chance. All right, so think about this for a second. What's the percent chance of having a boy? So you have a married couple, and they're having a child. What's the percent chance of having a boy? All right, well, hopefully you know that the percent chance of having a boy is 50% every time. So there's 50% chance of having a boy, 50% chance of having a girl. But here we have Jimmer and Francesca. They have 5 children, all are boys. Does this mean that our genetics calculations are wrong? Well, no, because each of those children had a 50% chance of being a boy. Now, that means that this is a sampling error. That means in this relatively small sample size, these people all just had 5, this couple had 5 boys. If you look at a class, you might not see a 50-50 ratio of boys to girls, but by the time you look at the really large sample size, you're going to see a 50-50 ratio or near 50-50 ratio of boys to girls. All right, this is the type of sampling error. So let's think about this for a second when we flip 2 coins. All right, what are the chances of getting 2 heads? What are the chances of 2 tails? And what's the chance of 1 of each? Well, we can actually think of our coins as almost a Punnett square. You have 2 alleles. You have a head and a tail on each of those coins. All right. So you can flip 2 heads. You can flip a head and a tail. You can flip a tail and a head, and you can flip 2 tails. So we basically have a 25% chance of 2 heads, 50% chance of 1 of each, and 25% chance of 2 tails. But if you do that a relatively small number of times, you may not get that ratio. That's a sampling error. You haven't done it enough to see that full ratio. You would have to do it a lot of times to really get that. All right, so what I want you to do now is go back to Canvas and really go on to the activity. And there's a random coin toss online that you can use, or if you have 2 actual coins, you can do that, whatever. But you're going to record on the spreadsheet, you're going to record your data. So you're going to toss 2 coins 10 times each, and you're going to record the number of times you get 2 heads, the number of times out of those 10 you get 2 tails, and the number of times out of those 10 flips that you get 1 of each. All right, so go ahead and do that, and then we will regroup.